What I'd like to explain in this video is how we move financial contracts and other sorts of contracts, other sorts of programs to run in the context of a blockchain. And if you remember when we talked about blockchain in general, this was the summary we had. What we have on a blockchain is an irrefutable record of transactions. So these are, once a transaction is on the chain, it must stay there, it will stay there, it can't be modified, it can't be removed. And the chain itself checks that, provides a whole lot of services. It allows us to be sure that when a UTXO is redeemed, it's only redeemed by somebody who has the authority to redeem it. That the process of validation ensures the integrity of the blockchain. But on the other hand, we learned that the chain is passive. So the chain is built up of transactions, but any transaction is created off-chain and submitted to the chain. So there are things we'll have to think about off the chain as well as on the chain. And in particular, we have wallets, which are the places where people keep, retain any assets that they have, and we'll need to, as a contract will potentially transfer assets, then we'll need to think about how those processes are mediated, how we write contracts that work in this world. And we have to think about incentivization. We have to keep the chain alive, keep the contract alive. The particular context we're working in is the context of the Cardano blockchain. It has the ADA cryptocurrency, though Marlowe could equally well be implemented on top of a blockchain like Ethereum, which is based on accounts. As I said again in the introduction on blockchain, what we have here is a UTXO model. It's somewhat extended in a way that I'll explain in a couple of videos' time. But the model is this of assets flowing along what looks like a data flow graph. Assets flowing from one transaction to another. The black outputs are spent on becoming inputs of further transactions. I've been working on Marlowe for a number of years. First of all, when I was an academic at the University of Kent, and I was provided with research funding by IOHK. And one reason I was keen to work with IOHK was the fact that they make all their work open source. So you can look on the IOHK repositories and you can find the source code for Marlowe, but also for all the other parts of the Cardano blockchain. So IOHK are open source about their code, but also they're very keen for us to write papers. And so there's been no tension between working with IOHK and free dissemination of information. And I think the other feature that I think it makes working with IOHK so interesting is that they've got a strong commitment to functional programming. So if you look at a typical contract on something like Ethereum, there will be some of the code will be written perhaps in Solidity, the on-chain code, but the off-chain code may well be written in something like JavaScript. Whereas the way that the Cardano blockchain works is that everything is written in a variant of Haskell. And let's look in a bit more detail about what the Cardano blockchain looks like. It's got the settlement layer, which is the fundamental blockchain, the point at which assets are transferred. Assets are transferred from a UTXO to by spending that UTXO. The general purpose scripting language in the Cardano blockchain is called Plutus, and Plutus is really is Haskell, which is compiled down to work on as a scripting language for Cardano. Now, what we've done is building on top of Plutus. Marlowe, in fact, is a complex Plutus smart contract. We've built our special purpose domain specific language, And as you can see from the diagram, this is embedded in Haskell. So Haskell pervades the programming aspect of the Cardano blockchain with general purpose facilities provided by Plutus and special purpose facilities by Marlowe. And as you can see there, that I've also shown that we need to link the real world to Marlowe, potentially through receiving deposits or getting information from the world about the price of a particular stock or of crude oil or whatever. And also it needs to be linked to users' wallets so that assets can flow in and out of running Marlowe contracts. So that's the general picture that we have. That's where Marlowe sits in the blockchain ecosystem. Now, what happens when we move things onto blockchain? Well, we have to think differently about how contracts are enforced. A non-blockchain contract, in the end, is going to be enforced by a legal system. The contract is not self-enforcing, but the world of blockchain, the world of distributed ledgers, is one where there may not be any authority to ensure that the contract is enforced. Now, you could say one view of that is to say, oh, okay, that's fine. What we'll do is the blockchain will be there to record transactions, to record what has happened. So it will provide an auditing, an automation facility, but it won't necessarily enforce that the conditions of the contract are adhered to. But we can also try to think about how we might using crypto economics, using the right set of incentives, might be able to ensure that the contract is as self-enforcing as it can be. So that's a new dimension we have to think about. The other intriguing thing about difference between the blockchain world and the financial world is this question of double spend. Now, of course, we don't want blockchain is when we're thinking about cryptocurrencies, we want cryptocurrencies to behave like real currencies in that money can't be spent twice. If I have a £10 note and I spend it, that note is spent. I can't then spend it again. But of course, in the financial system, banks do spend money repeatedly, or any source of credit is effectively, in one sense, a double spend. In principle, and this is what happens when there's a run on the bank, money has been spent, has been lent to people multiply, and it's impossible to pay back all that completely. So, and credit is one of the engines of the financial system. So we need to be aware that if we want to use the blockchain as the place where the site for financial transactions, we have to be aware that we can't model things like credit on a blockchain. Any source of credit has to be external to the blockchain itself. In thinking about how contracts operate, we need to think about the modality of those operations. Now, a contract can make some things happen. A contract can make a payment happen because the contract contains the contract can initiate that action. But of course, a contract can't force a participant to make a deposit. So there is a different modality. Some things can be pushed, as it were, payments, but other things we have to wait for. The contract has to wait for an external participant to make something happen. And just in thinking about making sure that contracts behave as they should, we have to think, and I talked a bit about this for the general blockchain, but it applies equally well here. We certainly want to avoid bad behavior. We don't want to be able to spend money twice, for example, but we also have to make sure that good things keep on happening. We have to avoid a situation where we have to try to avoid as much as we can, the situation where participants withdraw from a contract. They simply stop interacting with the contract. So we have to find ways of dealing with that. So we have to think, we have to model, we have to get a sense about how we might get values from the outside world. Perhaps we need random values if there's a degree of randomness in the contract, or we have to get values of oil stock prices or oil spot prices or stock prices or whatever. Now, it isn't in a sense up to the blockchain to provide those, and we can, as far as our model of how things work on the blockchain is concerned, we can simply think of these as another participant in the contract performing an action. They're providing a value, just like the human participant might make a choice. This what we might call an oracle is doing something very much like that. So the way we deal with this in Marlowe is to treat them as, when we need to, as participants. Now, the other thing we need to think about, and this is perhaps at the core of what we're doing, we need to think about money being committed to a contract only for a finite time. So the money can't be locked forever. And this gives us a way of avoiding somebody simply, if I had a contract with you, you commit some money to the contract and I simply walk away. In theory, that money could be locked up indefinitely. Our contracts need to ensure that that can't happen. So we need to think about timeouts. Our contracts need to talk about ensuring that after a clearly defined amounts of time, money can be released. And as I said earlier, we can't require a deposit. We can only ask for a deposit. Ask for someone to deposit a certain amount of money in the contract. Now, if we do that, we run the risk of having to wait forever. So we have to think about asking for a deposit, but only waiting a certain finite amount of time to do that, and then taking some remedial action if they haven't made a deposit by that time. So we use, in order to get urgency, in order to make sure the contract keeps on progressing, we ensure that every operation that waits for something from the outside world will only wait a given amount of time. And this means we can look at a Marlowe contract and we can see that it will have something like an event horizon. After this amount of time, nothing more can happen in the contract. So we can see that at that point, where nothing else will happen, we can quite happily, and this is part of our model, refund money, any money that's left, refund it to the people who deposited it. Okay, so I hope that gives you a general picture of how we approach moving to the blockchain world. What we'll do next is we'll look at our escrow contract and see how that has to be modified to fit in this new world.